It's 1 o'clock, so I'm going to start the class, and I'm going to talk about a new topic. It's on non-parametric estimation of the distribution of the data. Non-parametric. And I'm going to introduce 3 ways of estimating the probability distribution of the data. Many of our problems require the distribution of the data, and very often we have no clue what the distribution of the data is. So we either use a model, for instance a Gaussian, and we estimate the parameters, or whatever distribution that we know, estimate the parameters. Or we can estimate it another way, where the distribution is not parameterized. There's no parameter. And so I'm going to introduce 3 ways of doing this. This is nothing really new. It's in many, many textbooks. It's really not machine learning. There is another field called non-parametric Bayesian learning. And the use of non-parametric here is completely different from the non-parametric that's used in the density estimation context. Okay? So this has nothing to do with that. Okay? And I'm going to talk about some methods, and one of them will be estimating the distribution based on the histogram of the data, and another is the kernel. And I should tell you that kernel, definition of kernel, is used in many, many different fields. People who are studying operating systems use kernel in a different context. Even within machine learning, the kernel that's used here is very different from the kernel that we will use later on to talk about support vector machine. Okay, so keep that in mind. So let's just read what this is. This is supposed to be a very, very easy lecture. Okay, very easy. One of the easiest lectures to understand. So pay attention. Last week's lecture, or was it Monday's lecture, was a little bit difficult, I guess. So that's why we got all these people dropping the class. So hopefully, it will be a sort of a feedback system. Whenever I feel that there is too many people, then I make it hard, and whenever I see that there are a lot of people dropping, then I make the lectures a little bit easier. Okay, so this is an easy lecture because we lost a lot of people. So, so here it is. What if you don't know and don't have a clue what the distribution of your data is? Okay, and so you don't know whether to put a parametric form in there or whatever, Dirichlet, binomial, you have no idea. So what can you do? And right here you can do a lot. And one way of estimating the distribution, this is probably the easiest way, is based on the empirical distribution function. Okay, this is the first. I'm going to introduce 3 methods. This is the first method. And what you do is, so for your cumulative distribution, I hope everyone knows what a cumulative distribution is. 누적. Okay, so it's defined as the probability of x being less than some value x. Okay? So what's the probability that it's less than 0.5? That is what cumulative distribution is. Okay, 누적 확률. And density is, what's the density? The probability of x being within x and some small addition of that. That's probably density function. Okay, so I hope you understand this. So one way of characterizing the data is by the CDF, and it's very simple. Here is the rule. Here is an estimate. It's a function, CDF is a function of x. It's a function of what this value is. Okay? What this value. Is it going to be 0.5, 0.3, 0.2? What's the probability? That's what it says. So it's a function of x. And we have, in machine learning, as we said, we have training data. And we find out how many of the elements are less than x from our training data, and divide it by the number of elements. Okay? That's easy. That's how we do estimate the CDF. And you can see that it's a function of x again, and it's also a function of the number of samples that you have in your training set. Okay? And mathematically, you can write it using an indicator function, I. Here, I hope you're in machine learning, we use a lot of i's. Whenever this is true, it takes on the value 1. When it's not, then it takes the value 0. So when xi, so these are training samples, when xi is less than x, it's a function of x, you set x. If it's less than x, then actually when it's true, it's value 1 in this case. And when it's false, it's 0. So I should make this clear. Here, I is true in this case. Then it takes on the value 1. Otherwise, it's 0. Oh, wait a minute, sorry. A is true. Otherwise. The training sample is less than x, then you count that as 1. If it's not, then it's value 0. Okay, and so this is how you characterize your training data, the distribution, very easy. Now, what sort of property does it have? Okay, the expectation of this function is fx. What does this mean? Expectation of f of x. So if you take, so this depends on what? It's a function. It depends on and what? What your training sample is. Okay, your n training sample. If you take all different, many different samples that you have, if you take the average over it, okay, the average is the true cumulative distribution. This is the true cumulative distribution. Okay, so the average is the cumulative distribution, and the variance of this function. So you change the training data, okay, the training data, and you find out how far you are away from this true function. And you take the square, then you arrive at this thing here. Okay? So this is the amount of variation that you may have depending on the training data. The training data that's given to you. Okay, you may be off by this much. And if you look at this, if n, if you have a lot of training samples, okay, if you have a lot of training samples, what is this variance? What does happens to this variance? It goes to 0. Okay, so that's another nice property. So by strong law of large numbers, this goes to that, almost sure for fixed lengths. So point-wise, for a given x, as you increase n, this approaches fx for each of the points. And this almost probably sure it's a defining probability, okay, by epsilon. And I don't want to go into details of this. If you want to find out a little bit more, it's just not word, but it's a mathematical term, okay, probabilistic wise. Okay, so that was the first method that I wanted to tell you. You might have already seen it. The second method that I would like to introduce to you is based on the histogram density estimation. Okay? So you have training data, and of course you assume that each of the training data are IID, meaning that one data is not dependent on the other. Okay? And let's assume that each of the training data is between the values 0 and 1. Okay? And this is with, it's not specific to this case. You could make your training data look like that. Very easy. How do you do that? You just divide it by the maximum value of some sample, and you can make all the training data and you scale it, you bias it to make it between 0 and 1. Okay? So this is the assumption. And it's very easy to satisfy this assumption. Okay? Then, in histogram density estimation, you define bins. Okay? And so for bins, you have to set a number m, some number m, into some number, let's say 10. And what this is you're dividing up, so all the values of the training data are between 0 and 1. So you choose a number m, and what that m says, divide up the 0, 1 region into m bins. Okay? So you've got 0 to 1, the data is going from 0 to 1, and you're dividing it up into m regions. So it's from here to here, 1 over m, 1 over m to 2 to the n, 3 to n, and so forth, n minus 1, 2, and that's 1. Okay? So we call these bins. Okay? So, and we call each, so this one is called B1, B2, and Bn. Okay? And we also, if we define Bm, we also know the bin width. We call this the bin width. And we denote it by an H. Okay, it's M over 1. So we divide up the 0 to 1 into m bins, and then we have training data, and we allocate the training data into each of the bins. Okay? And the number of training data in the bin is denoted by V. Okay? So Vj is the number of training data in bin J. Okay? Number of observations or number of training data allocated to bin Bj. And obviously, if you add up all the number of data into each of the bins, it all adds up to 1. Okay? We can also estimate the probability of a training data being in that bin. We have n training data, and the probability of being in that bin, okay, an estimate, would be n over Vj, right? This is the probability, estimate from the training data, probability of being in bin J. That's that. And that's an estimate based on your training data. In reality, it would look like this. Let's say we have the probability, true probability of the data. True probability of the data, that's Px. And we know which bin, Bj, right? So we just integrate this probability. It's a probability density function. This is a probability density function. Okay, don't confuse with cumulative distribution function. Probability density function integrated over the correct region. That's, we call that Pj. So the difference between here and here, this is the true probability in being J, and that's your estimate based on your training data. Okay. Now you can assume that you have a training data, so n training data, being in that you're either in the bin, or you can think of it being not in the bin. Okay? So this, you can think of it as a binomial distribution. Taking a data, is it going to be in here or not here? So what's the probability of hit there? Probability of data being in bin J, it's probability Pj. And what's the probability not being in there? 1 minus Pj, right? And you have n number of them, okay? N number of them, so it's a binomial distribution, and we can see that the mean value is going to be n times Pj, and the variance is going to be that. Okay? Just to remind you, binomial distribution says how many hits or how many ones are there with n, if you do n experiments. Okay, so that is that. So your estimate based on n training data, your estimate of the true probability density function is given by this thing here. So it's divided into m bins. X is n bins. X can be either one of these m bins. And what is the probability of that being here? You divide it by p hat divided by h in width. Okay? So the probability of being in bin B1, it would be this times the bin width. What is the bin width? This is the probability. This is the probability density function, I should say, to be correct. Probability density function. What's the probability of being in the bin? You have to integrate this over the bin. What is the bin width? M over 1, right? Or h. So you multiply by h, you get probability of being in that bin. So, okay, everyone understand what I'm doing right here? It's very simple probability. Trying to make it so easy so that we won't have more dropouts. Okay? Now, so this is my estimate of the probability density function. Okay? Now, I want to find out what is the characteristic of this bin estimate using that. So I'm doing an expectation over this. Okay? So this is saying, if I change the training data, what is the average? If I change it many different training data, what is the average probability? Okay, and then so you plug in one of these things in here, and then you go through this math, and it's almost, with various approximation, it's Px. Okay? So if you have many training datas, different sets of training data, and you take the average, then with approximation, it's the true probability density function. So this is the second method, another very easy method for estimating the probability. Now, but if your professors or someone says, okay, do this, you estimate the probability using histogram. And you start doing it, and then the first thing that you have to decide, what's the size of the bin? Size. What's the bin width that I'm going to use? Okay. And it turns out, if you have too many bins, you're going to have high variance. What does this mean? High variance. I've said this many, many times from lecture 1 to throughout. Overfitting, but I want something else. It really depends on the training data. Okay, if you have many, many bins, and so you're not really having, you only have 1 or 2 in each of the bins. Small number, because you have so many bins. So you can't really take a statistic. You have to have like millions. 2 million, then it's going to be sort of robust. But if you have too many bins, at each of the bins, you're going to have small number of training data. What does that mean? If you change the training data, what happens? Your estimate will change greatly. So it's high variance. Okay? Let's say if you have 1 bin, if you have less number of bins, what's going to happen? Let's take a simple example of 1 bin. 1 bin. Even though you change your training data, the average is going to be pretty much the same. Okay, so what can you say about that? Even though you change your data, your estimate is going to be pretty much the same. What does that mean? What's the terminology that you would use? Low variance. Okay? Low variance. It doesn't really depend on the training set that you have. But it's high bias, meaning that the true probability has up and down, has some very flexible shape. Few bins cannot model the complicated shape. It's not flexible enough because the number of bins is so small. Okay? So that we call that high bias. So you have too many bins, high variance, too small number of bins, variance and bias trade-off. So what is the appropriate number of bins that you should have? So many people will just, try scan the bin width, and try to find an appropriate. But rather than doing that, okay, let's go through some analysis. Okay. So here is the average, here is actually the variance of the histogram. Okay. And my measure, what I would like, is my estimate using N training data, the true estimate of the probability, the difference between them, square that, and I want to do it for all region, and I want to look at that measure, and I call that measure L, and it's really a function of H, okay, the bin width size. And I want to do it what? I want to have a very low value. I want this function to be close to that for all regions that I'm considering. Okay? Everyone understand this? So now I work out this square thing and I get this. And I look at this. This thing, this last thing, I cannot do anything about because that's fixed. For a given probability, this is probably fixed. Okay? This I can probably do something about. And let's look at the midterm. It's -2, average, weighted by the probability dx. Okay? Over all regions. So what does that mean? So this is, it's written down here, it's the average height over the estimate. Because you're taking the average, if you multiply this by the probability and you integrate it over, you're taking essentially the expectation of this. Okay, the average of that. Okay? I could do probability average, or I could take the sample average. Okay? So this is the average value for each of the training. Okay? So, okay, so I want to minimize this. I want to minimize LH, which is a function. Is a function of H, and this last term really doesn't. It's not a function of H. It's only these two. So I take that. Okay, so that's a good measure. I want to minimize this, but I don't have this. I cannot take the average over my estimate. Okay. I need to somehow approximate this. Okay? And the way I approximate it is by the sample average. So I bring the -2 right here like that. And I do some kind of a sample average, so I divide it by n over all the data. Okay? And I want to, so I'm taking, rather than taking it over all integrals of x, I'm taking sample average now. Okay, remember? You know, you do this very often. You want to take, you approximate some process. You want to take that, but you do it using sample average, time average. Okay, I can't think of one right now. Instead of taking this average over x, all x, you take the sample average. And that's what we're doing, sample average here. And the way we do it is by this. I have a -1 here. What does this mean? So the way I'm going to take the sample average is I'm going to estimate this leaving out the ith training data. Leave out the ith training data. Use that as test data. With the n-1 training data, so I left one out, I do histogram density estimation. And then I substitute my ith training data into the histogram to find out the probability. And I do it for all the training data. Okay, everyone understand what I did right here? Okay, so if I have n training data, that's 10 of them, I leave this one out, and I take 9, and I do a probability estimation based on this 9. Okay? And then I take that one, I take the one that I left out, and put it in, and find out the probability. Then I leave out the second one, and then based on this, I do a probability density estimation. And then I find out what the probability of that is. And then I go on for all 10 of them. And that's how I do my average. Okay? So now, then I define this term as JH. It's a function of h. Okay? But it's a quantity. It's a quantity that I could estimate. Okay? And it's a quantity that I could minimize over the h value. Okay? So the value of h that minimizes this quantity is the h that I should use for my histogram estimation. Okay, everyone understand what I've done right here?
근데 적분에서 밑으로 가는 에스티메이션이
어떤 거? 이거?
잘 맞는지 아니면 그런 거는 어프록시메이션이 잘 된 건지
잘 approximation이 됐는지 I don't know if there is a proof for this, but this is just one way of estimating. Okay, we want to you want to get this quantity without having px, and this is probably one way of doing it. And so far, by practice, it's a very good way. Practice-wise, I don't know how close this is. Okay. And that would also depend on how many ends I have and so forth. Okay, and so this is a thing that I would use to find out, determine what is the appropriate number of h. Another way is, there are two ways. This is also, I don't know, it's from some paper. I'll try to find out where the, I'm sure you could, if you do Google search on histogram distribution, then you can probably find out where I got this equation here. So this is another way of estimating JH was given by this equation. Okay? And I forget how this was derived, but this is another equation that people use to find, to minimize, in order to find the appropriate value of H. Okay? So this is another way of doing it. Another very easy way is just do this. This is the second term. You leave out the ith one, minus I means training, you leave out the ith training data. You estimate and then find out the probability of that piece I left out. And you take the average. And you find one that gives you the best H. Okay? So that is my second method. Okay. And this will be my last method that I want to introduce to you. It's called kernel density estimation, or some people call KDE. Many of the old methods, old books on pattern recognition call it Parsons window. Parsons window. Anyways, it's called Parsons window, right? Okay. And this tends to, it leads to a smoother and faster convergence than the histogram. Convergence meaning that as you increase the number of training data, we see that our estimate of our density function approaches the true density function. Okay. This kernel density estimation method approaches the true at a much faster rate. Okay. So for this, I define, or here is defined a kernel. And here is the definition of a kernel. And here it's not to be confused with the kernel machine that I'm going to be talking about later on. Okay. It's different kernel. And the kernel that satisfies three properties. One is that it's always non-negative. Second, if you integrate it, it equals to 1, so it has a probability. And if you take the average, it's 0. So it's centered around 0. Okay? And one example of a kernel is this Gaussian, with 0 mean with unit variance. Okay? This is an example of a kernel. Very easy. But there are many, many, many different types of kernel. I want to introduce you to another kernel. It's called the Epinishnikov kernel. And this is the kernel that is preferred in machine learning for various reasons. And one of the nice reasons is that Gaussian has infinite support, meaning that it's from minus infinity to infinity. Okay? And my data, the true data that I have, may not run from minus infinity to infinity. Okay, it may be from a certain region. And if I use Gaussian, then it's going from minus infinity to infinity, and it's very difficult to use in that case. So, definition of Kopf, it looks like this. Okay? It's a quadratic. Okay? And it's a cup upside down. Okay? And it has a maximum value at a half. No, at 0, I'm sorry. At 0. So once you have this, what do? You do this. This is the equation for my estimate of the probability density function. And what have I done here? What have I done here? I took these kernel functions, either Gaussian or Epinishnikov, and I put it on each of the training data, like a hat. Each of the training data is at its position, okay? And you give out these hats, and everyone's wearing the Epinishnikov or the Gaussian hat at that location, okay? Everyone's doing it. And then you scale it by h. Okay, here's also a scaling factor. Okay? So if h is 1, greater than 1, less than 1, depending on what h is less than 1 or 1, what happens to the hat? It goes wider or narrow like that. Okay? Depending on the h value here. And you scale it. So each of the training data is where it's at the position, and then you put the hat on each of the training data, and you also scale the hat, okay, for all similarly. And you average it. You need to have this, okay, if you scale it, you have to scale it equally outside by h of 1. What is this? Why do you need to have it like that, h of 1? Okay. What's the reason for having this? Why? This has a nice property. This k has a nice property. What property does it have? It's like probability. Okay? And we're doing it for all training data. So we all training data, but you're taking average, so that's okay. But if you scale the inside by h, what happens? It grows. The integral of this becomes what? H. So you need to divide it by h. Okay, so that's the scaling factor. That's all on the next slide. So, so when h is small number, you get a very sharp. The hat is very high, tall hat. H is small. When you have h is big number, then you have a sort of a flat and wide hat. Okay. What would you use for h? What sort of advantage and disadvantage would you get from choosing different h values? 어느 경우에 h가 이런 단점 있을까요? So whenever I ask a question, everyone starts to looking at their paper. When I'm not asking, they're looking at me. Okay. When you have a high concentration of data in certain location, lots of data nearby, you really want to get a detailed estimate of the distribution. Right, the data is very, very close. So you can get a very detailed distribution, the shape, fine shape. But if the data are really far away, because the data are far away, then you probably want to have these kernels spreading out far. Okay? So it depends on how your data is distributed in the space. So is this okay? So this is an estimation of this is kernel density estimation. Okay, this is an estimate of the probability density function. And people ask, well, does it really depend on what k I choose? Is it better to use Gaussian or Epinishnikov, or there are others? But really, the difference is not much. But Epinishnikov is between 0 and 1. Gaussian is far. So depending on your application, you would choose one or the other for those things. Okay? And here is Epinishnikov is optimal, and people have done some weird analysis and have said that this Epinishnikov is close to suboptimal in certain sense, theoretical sense, but it's not. It's too theoretical for me to tell you. Okay, so that is that, and let's see. So final form right here. Why is H1 needed right here? Tells you that. And so there it is. Now, so in this third method, we also have to. Someone says, okay, now don't do histogram, do kernel density estimation on the training data. So this is very, very easy. You just put Epinishnikov or Gaussian on each of the training data. But you're also faced with a dilemma now. What is the dilemma? Or what H should you choose? H. What is an appropriate value of H that you should choose? used. And for this, someone has actually calculated or did some analysis, very, very complicated analysis. Not very, very complicated, but long, very long. And actually, the proof is, if you read this, the proof is here. Okay, and the JH meaning that the distribution of the estimate and the true, you want to minimize the mean square error. Okay, the difference squared, minimizes. You can approximate it looking like that. And you see that there's K 0 there, K star, but that's already defined right here. Okay? In terms of the kernel. All that definition is done. Okay? And so here, if you're using KDE, you look at this function using, substituting this in there and that for that, for 0, you put 0 here, and so forth. And you minimize this, find the H that minimizes this. And you find the appropriate H and you set it. Okay, so which should you choose? So I'm comparing histogram. I said histogram and the kernel density estimation and the parametric. Okay, and this is order. N is the number of training data, and that's how fast it's converging. Which one is converging the fastest of these three? Which one is converging fast? Well, with increasing training data towards the true density function. Which one? Parametric. Then it's kernel, and then history. Okay. And obviously, parametric, almost the shape has been worked out for you, right? And as you only need to estimate the parameters, and you're going really. If you're going, if your parametric is in the form of the true density function, then it's going to go really fast, much faster than kernel densities. But we do non-parametric density estimation because of what? We don't know what the distribution is. We have no idea what it is. So that's why we use non-parametric. Okay? If density of the data is different in different parts of the space, you may want to use a variable width. So certain, as I said, here you have data. Like that. If the data is spread out this way, this is what I mentioned. I probably want to put definition of power for whatever on right here. And I add all that. And here I use long ones. Long ones on them to get general distribution of this data. And here is some data that generated. You can generate data that looks like this. In MATLAB. So MATLAB has a function that can give you data that follows a Gaussian distribution. And here is Gaussian distribution first parameter here says the mean value. And the second one is the variance. And I have placed weight 0.3, 0.4, and 0.3 on each of them. And that's the distribution. How would you, if I had a Gaussian, I have a program to give you samples of Gaussians. How would I generate this data? How would I generate this data? I want to find a data that follows this distribution. So it looks like this. If I draw it, it looks like that. I want data that follows this distribution. How do I do it? So it's 3 Gaussians linearly combined. I want data that I want data that is distributed this way. How would I do it? Some points, I can give you some additional points on your exam, which will be in 3 weeks' time. 3 points if you answer it correctly. Okay.
지금 0부터 1까지 사이 중에 유니폼 디스트리뷰션에서 랜덤 넘버 만드는 것도 쓸 수 있는 거예요.
아, 그렇습니다. 네, 그렇게 할 수. Okay, that's okay. So I should have said MATLAB gives you 2 sampler, I should say. It has a function that gives you data that follows a certain distribution. It can give you data for Gaussian and also for unit. That's right.
그럼 먼저 유니폼 디스트리뷰션에서 0부터 1까지 중에 하나 골라서 0부터 1 사이 중에서 이제 랜덤 넘버 하나 한 다음에 그게 만약에 0부터 0.3까지면 저 첫 번째 노멀 디스트리뷰션을 뽑고 0.3에서 0.7까지면 저 두 번째 노멀 디스트리뷰션을 뽑고 그다음에 나머지 0.7에서 1까지면 세 번째 노멀 디스트리뷰션에서 뽑으면 데이터가 나올 수 있어요.
Okay, and then 그리고 그다음에 거기에 해당되는 Gaussian 해서 central of them.
네.
Okay. So this is what it is. Okay, you're correct. So here, if you look at the numbers here, the coefficients, 0.3, 0.4, 0.3, obviously they have to add up to 1, right? Because if I integrate the Gaussian just by itself, this equals to 1. 1. So I have 3 Gaussians that add up to 1. So I put some number here, and this number, each one of them would also have to add up to 1. Okay? So now I have 3 Gaussians. Okay? And the way he said it, I choose now. Of the 3, I choose either one of these 3 Gaussians to get my data. So my data, 30% of the time comes from here. 40% of the time it comes from here. 30% of the time it comes from here. So that's the meaning of this distribution. So I have, MATLAB can give you a random number between 0 and 1. 0 and 1, right? So if it's, the random number is between 0 and 3, from 1 to 0.3, then I choose this one. If the random number is between 0.3 and 0.7, then I choose this Gaussian. Then from 0.7 to 1, I choose this Gaussian. And then I have sort of randomly sampled the data. Okay, so it's a two-way process. You do uniform sampling, random sampling, and then sample from that appropriate person. Okay, you understand what I'm doing?
교수님 근데 저게 가우시안의 리니어 콤비네이션이니까 또 다른 가우시안이잖아요.
이 세계 가우션, 세계 더하면 또 가우션이야? 이렇게 이 모양인데 가우션이야? 근데 가우션 같이 안 생겼는데.
저게 각각 n0 그러니까 각 가우시안 3개 중에서 각각 랜덤 베리어블 뽑은 다음에 0.3 곱하고 0.4 곱하고 0.3 곱해서 더하는
그 얘기는 아니에요. So remember what I said about this thing? X coming from here? I've already mentioned this in my first lecture of the notation. No? This is distribution. That is sample. This means if I do this, X is sampled from this distribution. And just, if I say it doesn't, how can you interpret 0.3 times multiply a distribution to be an output times 0.3? Doesn't make sense. 이해하셨습니까? Okay? So I have training data. Okay? I have lots of training data. I get N training data. And let's say I forget what this was. I have no idea. I forget. And so I use either one of those three methods. Okay? The empirical density estimation histogram and the kernel density estimation. And here in this example, I'm going to use this one right here. What is this called? The kernel density estimation. And I'm going to use Epinishnikov kernel for this. I have lots of training data for this. I can get it lots of training data. Okay, training data is given. So I have n 20 number of training data, 200, 2,000. Okay, and this is different values of age. Not a very good estimate. H5 maybe a little bit better. And then as I increase the number of samples, the appropriate one, you see if H is too small, when it's very, very noisy, not smooth. If H is appropriate, then it follows the true distribution. And if H is too big, then it's very, very smooth. Okay, it doesn't have the details of the true distribution. Okay. And here, I choose H based on this thing right here. But for data set 3, meaning that I have 2,000 training data, I take each one out and I estimate the probability distribution, and then I plug in the probability, and then I average it. And this is the function that I got for different values of H, and this is the value of this. Okay, so some small value less than 0.2. rises and then starts to drop. And we found out that point was 0.1 H. And using that, this is the estimate. The blue one is the estimate that I got. Okay. So today's lecture was very, very easy. I'm done. I'm 15 minutes ahead of my time. Non-parametric density estimation, histogram estimation, kernel density estimation. Any questions? If that, okay. So I have some. 이게 뭐죠? Oh, I have some 6. So maybe I'll do a little bit of 6 then okay, that's non-parametric density estimation. Okay, non-parametric. I want to emphasize non-parametric is used differently in machine learning. Right now, non-parametric Bayesian learning is very popular. BMOSU. It's called BMOSU Bayesian. That's a really hot topic, and it's non-parametric. And the non-parametric there is different from the non-parametric here. Non-parametric Bayesian, you have infinite. You have the number of parameters is equal to the number of training data. Okay, but that's a little bit high level. Okay, now let's look at very important method called expectation propagation. Okay. I have a little bit of time, so I want to do this, and maybe I'll have an easier time next time. So the algorithm that I'm trying to introduce, you've probably heard it, is called EM. Expectation maximization. Okay. It's used in many places for estimating the parameter. Okay, it's a method for estimating the parameter. We learn maximum likelihood, maximum A posteriori. Now, maximum likelihood, you just find the likelihood function and then you try to maximize it, or by taking the gradient or something. Sometimes this may be difficult and you cannot work it out explicitly. And I'll give you an example, a very good example that's also given in the book, but I'll talk about that. And that's the case of the Gaussians, and I'm going to talk about that, and some properties, and then some worked out example for 2 Gaussian case. Okay, what is this? What are we doing? So this EM, expectation maximizer, it's a general technique in many parts of machine learning for getting the likelihood estimate of the parameter. And it comes up in mixture of Gaussians. Okay, we saw 3 mixture Gaussian example, and how that was. Rather than going through this, I want to look at this example right here. It's 2-dimensional. 2-dimensional point. It's point. And you can see the colors here. Each of the colors are from a different Gaussian. Okay? The red one, obviously, it comes from a Gaussian where the average is here, and the covariance is shaken right away. The green one has a mean right over here, and it's coming from here. The blue one average here, and it's coming from here. Now I have all three at one, so it's a combination. So it's three Gaussians, but weighted. What's the weight on this Gaussian? What's the weight on this Gaussian? It's the proportion of red over the total number of data. The Gaussian on this one is the proportion of green over all the data, and so forth. Okay? So just by looking like this, it seems like the red one is about 0.4, green 0.35, this one maybe 0.3. I don't know if that add up to one. But anyways, that's the proportion. Your professor or whatever your boss, senior boss at a company says, okay, I want you to estimate the distribution of this. And you say, oh, this is so easy. What you do is you just get the red ones, and you find out the mean and covariance function. Green one, so easy to do. Blue one, you just get the blue one mean variance. Very, very easy. And you can find out the proportion by just counting. A little bit harder problem is this thing right here. No colors. Three Gaussians. Three Gaussians. I want you to estimate the mean variance of each of the Gaussians and the weight. How would you do that? How would you do this? This one is easy. Okay? You just take the one. You know which Gaussian this came from. So you just that one and that one and that one. How would you do it in this case? And I want to just, today I got about 8 minutes, and I want to tell you about the philosophy, okay? Rather than going through the math, philosophy of EM, and understanding this algorithm. So what is this? How would you do this? In Bayesian, I would like to say, Bayesian, we are not sure about anything. We don't say, hey, that is 0.5. Or 0.6. We say, we give a function. Hey, it's like it's, we just give a function, like that. Let's say for a parameter theta. Hey, it's very highly likely it's 0.5, but it could be others, but with lower probability. That. Okay. This is machine learning. Okay. Bayesian approach. Based on that, how would you approach the right-hand problem in estimating the mean variance and the weight of the Gaussian? The insight here is for each data, there is a possibility that it's either one of these three. Okay? And we call that latent variable. For each one of them, denoted by Z. Let's say this is the ith data. Latent variable, ith data. It's a vector. Probability of red being 0.4, 0.3, and 0.3. Probability of red, probability of green, and probability of blue. Okay? For each of the training data, we assume that there is a latent variable associated with each of the data. Latent means it's unseen, it's hidden. Okay? Each of them has assigned this problem. It can be either of those three colors. Okay? Let's assume that I know these zi's very well. If I know zi, how would I estimate the mean value of the red one? How would I estimate the mean value of that one? For each of the data I have that. What do I do? I use all, here in this case, I only use the red one. Why? Because I know for sure that this one is red, probability 1, and the others is 0. This one, probability of red is 0, green 1, the rest is 0. I know that for sure. That's why I throw this away when I estimate the mean value for that one. Okay? Now, each of the dots can be any one of them, and it's given by this. How would I measure the probability of one of the Gaussians? Let's say the red one. How would I do that? I use all the training data, but for that one, I don't count it as 1. I count it as how much? Only 0.4. So each of the latent variable has only a proportion that I'm going to use in estimating that. And this one, this one is going to be available only 0.4 times in calculating the red one, 0.3 available for green one, and that one 0.3 in blue one. Okay? Once I have this, I can estimate all that. And likewise, not only mean value, covariance value, I can do that also. And I can also find out the weight of this. How much 0.3 on this Gaussian? Remember we had 3 Gaussians, but 0.3, 0.4, 0.3, the weight. I can also find that from this. Right? So now, I got 2 minutes left. This EM problem does this. Make an assumption. I start with an initial guess on each of the latent variables. Then I estimate the data based on these Gaussians. So I found the probability on this one, based on one of this. From that probability, what do? I do an update on finding the probability of the latent ones. Do that. And then from that, I can get the probability of each one of them and the whole thing. And get an update on that. And I keep on iterating until I find the maximum probability in representing this dots. Okay? That is what EM is. Not only for this case, but for other things. You want to hear, oh, I wish I knew this. Then I could, it's easy. That easy thing that's not shown is latent. You choose that as latent. Okay? And based on that latent, you make it easy, you find it, and then you update your latent. And you go back and forth. So that's EM, and I'm going to, next week, I'll talk about this a little bit more, and then I'll be done.
끊어야죠.